Okay, so depicted here we have a function which is, we're trying to find out if it's a solution to this right here. So in order to find that out, you have to ask yourself what is in this equation. So we have a second derivative of y with respect to x minus 2 over x squared equals to 0. So we're trying to figure out if 5x equals x squared minus 1 is a solution to this equation. So it should yield 0 in the end. When we take the first derivative, we get 2x plus x to the negative second power. We take the second derivative, we get 2 minus 2x to the negative third power. And after that, since we have our second derivative, we can plug it back into the equation that is given to see if it yields 0. Once we do that, we do a little bit of math, and we simplify to get 2 minus 2x to the negative third minus 2 plus 2x to the negative third. When these wind up canceling, these 2's cancel, so as well as this negative 2x and negative third and this positive 2x and negative third, which do yield 0, which gives us an explicit solution to this function right here. Okay, the advantages to an explicit solution is that they are the exact solutions to whatever equation you're looking at. And also, the equation is generally defined in terms of a single variable. Well, they always are. So let's erase that. So an example of this would be y equals y of t. Disadvantage is that you can't always find the explicit solution. Sometimes you only find implicit.
Okay. With implicit differentiation, you have a function defined in terms of two variables. So in this one, we have x squared plus y squared equals r squared, where r is a constant. But this depicts a circle or a sphere if you define r in terms of z. And when you derive this function, you're left with dy dx in terms of, you're left with dy dx, but this doesn't adequately describe the equation. So it can't be said to be an explicit function. When you derive x squared plus y squared equals r squared, you get dy dx equals negative x over y. And this won't tell us enough information to explicitly define a function. Okay, the disadvantages to implicit differentiation are that your function, your solved differential equation winds up becoming defined in terms of two variables. So if you have x and y, it's going to be in terms of dy dx instead of just with respect to x alone. From that, you can say that it's not very descriptive, because you can't just you have to have an output for y in order to plug back in for x, and then back again to get the next y in order to graph this function. So from that, I can say that it's very vague and very ambiguous. It doesn't exactly tell you much information about the solution. But some of the advantages are that from your dy dx function, you can find the tangential to whatever function you have. You can find whatever line goes along whatever curve you're evaluating, or if it's piecewise, whatever pieces you're evaluating. And it can serve as a general solution to your original equation. Okay, depicted here we have a graphical solution to a differential equation, where we can just say the function of t equals p. T being your x-axis, p being your y-axis. And we have all of these lines can be seen as implicit solutions to whatever your equation is. And this green line represents the path that this function can take. So this directional field yields all solutions for whatever interval you have in terms of your x and y. The disadvantages to graphical solutions to differential equations are that the graph isn't in equation form, so you don't have a written out equation for one to follow. There's also no direct equation, so you don't have an explicit answer to whatever equation you were solving. But the advantages are that you have a visualization of the solution, so it makes it easier for some to understand. It also shows multiple possibilities. The directional field shows all the things that can be and it also shows limits. So an asymptote will be directly visualized on this graph.